Complex can be complicated. Multiscale doesn't always mean fractal. Randomness often does play some role in the data that we look at. And algorithms as models often, quote, fly blind into the data. It's crucial that we measure an algorithm's performance. So again, what is a complex system? That big data tends to come from complex systems, many degrees of freedom, chaotic and regular variables, an underlying topology, strange attractor that's multiscale, and the ability to produce emergent behaviors. And of course, big data is what we tend to get from these complex systems. But a reality check. Multiple scales is not as simple as iterating scaled shapes. It doesn't require the same scaling at each iteration. So for instance, I have this structure here. It's not a fractal. I created this structure. It looks like what's called a Sierpinski triangle, but it's not. I used a different scaling at each iteration. So it is multi-scale. It is not a fractal. Doesn't require that transformations be used with identical frequencies. So let's look at an example of this by considering linear separation and the fact that it may be, even in an infinite dimensional space, it may be impossible to linearly separate two classes, even two-dimensional classes. So here's our scenario. Given the xy plane, let's think of it as the union of disjoint sets G class 0 and B class 1. G will be green and B will be black. And let's see if we can predict the class of a point xy chosen at random, given that the xy plane has this partition. The key here is that sets G and B may be too complex to allow definition of a higher dimensional embedding. Now, I say more in the next slide in the optional lecture. This is the optional lecture. So, how would we embed? Well, we could kind of define exactly what it means to embed. Given a point xy in either G or B, we could define a function c equals f of xy such that the new data, xyz, is linearly separable in 3 dimensions. And therefore, what would we want in such a function? Well, we'd want a function f of xy which first is accurate enough so that points x, y, z almost always occur on the correct side of the plane in 3D. In other words, we get good predictions from this scheme. It has to be simple enough to be calculated quickly. If it takes the age of the universe to calculate such an f, then we can't do that. And it has to be robust enough to allow small modification without loss of power. So there's another thing that we have to have, and that is this function f of xy must be created using a data set. So we use data because that's all we have is data sampled from the process. So let's see how this works. So suppose we had this partition, 4 green circles and everything else is black. Well, we would have a sampling of data, class 0 and class 1, and we would have to approximate the classifier scheme using, or the partition of the plane using the data. So given that data, we might cluster to find approximate centers of the circles. We don't really know the circles. All we know is that there is a 2-class partition of the plane, and we have to use the data to infer what that partition is. So we use the clustering to infer what the centers of some circles might be, and then we can estimate radii. So if we thought somehow this was 4 circles, so somebody told us that, we don't know exactly what size or shape they are or where they're located, but we know there's 4 of them. So then we can estimate the radii, And then we can define a function that's 0 if xy is inside one of the circles and 1 otherwise. And this would actually lead to a data set xyz for z equals f of xy, where in 3 dimensions we would have separable data. We could do this in higher dimensions using additional variables and functions. So we just did one f. We could conceivably define many of these helper functions and helper variables in doing this sort of process. But it doesn't always work. As a matter of fact, it rarely works. There usually has to be a very organized system when it does work, part of what we study in this class. So let's look for example, and suppose that we have points in the unit square are in class 1 if the point xy is leads to the complex number x plus iy, and in x plus iy the digit 1 occurs with a frequency greater than 0.25. So class 1, binary expansions of x and y, has the digit 1 with a frequency greater than 0.25, class 0 if it's less. And we get this shape. Now, if you had a sampling of data from this shape and you had to construct a function based on that data that gave you an accurate representation of this shape using linear separation in higher dimensions, you can see that either the function is going to take the age of the universe to calculate, or it's going to be too inaccurate and give poor predictions, or it's going to be so unstable that any small change or variation and it's going to completely not work. Likewise, if we had a classification problem where a point is in class 1, if Newton's method for z to the fourth minus 1 converges to a real root, given an initial point z0 equals x plus iy. So in other words, the point xy is class 1 if x plus iy as z naught causes Newton's method to converge to a real root. Otherwise, it's class 0. And now we see what's called a fractal basin boundary. And once again, any function that we would try to define, or any collection of functions, would either take the age of the universe to calculate or be unstable, because you would have to have essentially a data set the size of the xy plane, which is uncountable. So there would be so many points that calculating the function f would take so long it would be impossible. So you just can't use the linear separation for these classification problems. Complex is not random. It's a mix of chaotic and regular. Chaotic comes from deterministic, highly typical circumstances. In other words, it's natural. It's built into our number system. Even if it looks random, it's not, even though we may not understand why not. So here's periodic versus random. So 141 over 1,111 is a rational number. So it's a repeating decimal. So therefore you see a nice pattern. It's got what it's called a power spectrum, which is related to the period, how long it oscillates, and it's notice that it's 0.25 because we get a repetition. We've got 4 digits here. So if you have random digits, however, there is no particular frequency that stands out. There are no particular digits that stand out, and it looks something like that. Now if you look at square root of 2, both as a histogram of the digits and compared to the random digits, it looks very similar. So you might be led to conclude that the digits of the square root of 2 are random, but they're not. They're chaotic. It's unpredictable because it's a non-repeating decimal. But there's nothing random about how the digits of the square root of 2 occur. Same thing with e. We know exactly what e is, so it's got a pattern. It's just a pattern beyond our comprehension. Now, chaotic and random are not the same, but highly chaotic is practically random. Highly chaotic is high dimensional. Large numbers of unrelated independent variables acts like large numbers of trials of random processes. So chaotic and random are not the same. Randomness has a distribution but not a structure. Chaotic has a structure and a distribution. So what's the difference? Let's look at random versus chaotic. Random is non-deterministic, which means if you take a random process sampled exactly the same way in two different trials, you get two different sets of data, but you get the same averages. Deterministic, a chaotic process sampled exactly the same way in two different trials, produces the same data. Even the smallest variation can lead to significantly different, but if it's exactly the same, it's the exact same result every time. Randomness follows the law of large numbers. Isolated subpatterns are not significant because in the long run, only averages are meaningful when you're working in randomness. In chaos, each isolated subpattern of a chaotic process is information at some scale about an overall multiscale governing behavior known as a strange attractor. So, in summary, much of what we call randomness in the real world is actually chaos. Is it random or is it chaotic? Better question, is the data intended to reveal some aspect of a complex underlying structure? If yes, the question is a big data question. But we need enough data to allow for that complexity. And we need enough complexity to reveal the structure.